Welcome to the Modeler's Toolkit Definitions Zoning and Simplification for BAEM. In this introductory module, we are laying the foundation for effective building energy modeling. We'll start by clarifying the core terminology, the difference between modeling and simulation, and defining the key concept of a thermal zone. Well, we will then dive into the strategy of BEM, covering two crucial practical skills: how to effectively zone your building model and the rules for simplification. These are the decisions that determine whether your model is accurate, efficient, and defensible. This video is your guide to ensuring that when you transition a complex architectural drawing into a functional energy model, you are doing it with precision and purpose. So let's get started. Here is a look at what we'll cover in the next few minutes. We'll start with the core definitions and terminology, clarifying terms like modeling, simulation, and BEM. Next, we'll dive into the fundamental concept of the thermal zoning strategy. This is where you'll learn how to group rooms to save time and increase model accuracy. Then we'll cover model simplification and fidelity, the crucial rules for building a model that's accurate without being overly complex. And finally, we'll wrap up by looking at input data and reference standards to show you exactly where to find the trustworthy numbers needed for your energy calculations. By the end of this video, you'll be able to define the core terminology of building energy modeling, distinguish clearly between concepts like modeling and simulation, and precisely articulating the function of a thermal zone. These are the fundamental concepts that everyday modeler needs to master. Next, you will be able to apply practical strategies for building your model. This means knowing when it's smart to group several rooms into a single zone to save time, and when you need to simplify the geometry of an importer file to maintain accuracy. Finally, you will know how to locate the essential input data required for any energy simulation. We'll show you exactly where to find the reliable industry standard reference tables for the things like material properties, internal gains, and standard weather files. Before we dive into the technical definitions, let's start with a problem you are guaranteed to face as a modeler. Imagine this: you've been handed a beautiful detailed architectural drawing, a BIM file with over 350 separate rooms, complex roof details, and a massive internal atrium. The architect needs an energy prediction by tomorrow. Your software can import all 350 rooms, but if you hit run right now, you are taking a massive risk. What is the single biggest risk to the accuracy of your result? What is the finest strategy step you must take to simplify that 350 room geometry into a defensible energy model? This question forces us to think beyond simply drawing rooms. It introduces the critical concept of zoning strategy and simplification, the very things that separate a quick, useless result from reliable professional energy prediction. Throughout this video, we'll give you the toolkit to solve this problem, starting right now with some core definitions. So the problem we just discussed requires a precise set of tools and a clear language. Let's start by defining our core definitions and terminology. We often use the terms modeling and simulation interchangeably, but they have distinct meanings. Modeling is the foundational step. It's the creation of a mathematical or computer-based representation of a real system involving a series of assumptions and simplifications to convert a physical process into a computational one. Simulation, then, is the act of implementing that model to predict the system's future behavior. It's running the math. The broad field we operate in is building performance simulation, BPS. These umbrella terms cover the computational modeling of a building entire system. looking at everything from heat and air moisture and light. Our focus, however, is on building energy modeling, BEM, which is the specific process of using software to calculate a building's energy consumption and CO2 emissions. The key to BEM is the dynamic thermal model. Unlike simple static hour calculations, DTM repeats its calculations many times, typically on an hourly basis, to capture time varying factors like thermal storage, changing weather, and shifting occupancy. This makes the predictions much more realistic. Finally, tools like Design Builder act as a user-friendly graphical interface, or a GUI, that allows us to build and manage these complex models while leveraging powerful engines like Energy Plus. Now we move from definitions to the most fundamental concept in BEM, the thermal zone. What is a thermal zone? A thermal zone is a discrete volume within your model. It could be a single room or many rooms that we assume has a single uniform air temperature. This is known as the well-mixed air assumption. This simplification is necessary for dynamic simulation models, as it allows us to characterize the entire volume with a single point of evaluation for temperature and pressure. The main goal when defining the zone's geometry is to accurately conserve the areas and orientation of exterior constructions. Zoning is the strategic process of dividing your building into these zones. The right strategy saves time and ensures your model captures the crucial features. We used three main approaches. Grouping similar rooms. To reduce computational complexity, we merge multiple rooms into one zone if they share a few key traits. They must have a similar thermal performance, internal loads, and be served by the same HVAC system. The only caution here is that ignoring the lightweight internal partitions can sometimes slightly distort how the zone responds thermally. Second, we have subdividing a single room. Sometimes a single large room needs to be split into multiple zones to increase resolution. This is essential when you have large spaces where you expect temperature stratification, like in an atrium, or if you need to distinguish between areas with major difference in loads, such as the sunny perimeter versus the shaded core of an open plan office. And third, we have special purpose zones. Finally, you create zones for unique architectural features. This includes making vertical zones for atrium to model stratification, or creating separate zones for a large ceiling voids if they contain a lot of heat from lightning or are used as an air plenum. This level of details helps connect your model directly to the HVAC system design. We are now ready for the crucial third stage, which answers the problem we posed at the start: modeling simplification and fidelity. The strategic rationale for simplification is that your model's complexity must always match the design stage and the specific questions being asked. In early design, simplicity allows for rapid feedback and iteration, while excessive complexity wastes time, introduces errors, and provides little value. Always remember, a model is an idealized view of reality, not a perfect replica. The geometric strategy relies on the smart zoning we just discussed. You must use strategic zoning, grouping similar rooms or subdividing large ones to reduce the number of calculations. When dealing with important BIM geometry, you must also clean it up to remove tiny architectural details and ensure all surfaces are thermally robust, avoiding errors that come with overlay fine details. For physical inputs, we simplify the building fabric by using overall target U values, instead of meticulously modeling every single layer of material, especially early on. Likewise, don't model every bolt on a shade. Simplify solar shading elements to ensure the object casts approximately the correct shadow area, focusing on the essential thermal effect. Finally, operational data requires simplification because human behavior is unpredictable. We rely on standard schedules for things like occupancy and lighting hours. For climate, we use standard files like test reference years for annual energy calculations, which represent long-term average conditions rather than the unpredictable weather of a specific year. Now we know how to build a model. Let's look at the input data and reference standards, the authoritative sources for the numbers we need. For building fabric, you'll use overall U values and material properties for foundational standards. Your primary resources are the ASHRAE Fundamentals Handbook and ISO standards, like ISO 6946, which details how to calculate U values for opaque walls and roofs. For internal gains, you need to quantify heat from all the three sources. You'll find sensible and lighting gains from people in ASHRAE Fundamentals. For equipment and lighting, you rely on limits and power densities from sources like ASHRAE 90.1 LPD tables. Airflow and operation require two sets of standards. You set minimum outdoor air ventilation rates using ASHRAE 62.1 for commercial or 62.2 for residential. For all operating patterns, occupancy, lighting, and equipment schedules, you should base them on recognizing DOE reference buildings archetypes before customizing. Finally, for controls and climate, you set your thermal comfort goals using ASHRAE 55. Then you anchor the entire simulation using a standard repeatable weather file like a TMY or a EPW file, ensuring all your results reflect the correct climate. The workflow is simple. Start with authoritative handbooks and standards, save the schedules from recognized archetypes, and then localize with project or manufacturer data that keeps your models both credible and defensible. So to wrap up, we've covered a lot of ground today. Let's distill it down to 3 key takeaways that you can immediately apply to your modeling work. First, master the vocabulary. You must be able to clearly define VEM, VTM, and a thermal zone to ensure your entire modeling approach is technically sound. Clear definitions are the foundation of a defensible analysis. Second, prioritize strategy. Don't just import and run. You must apply strategic zoning and simplification rules, geometric, physical, and operational, to transform that complex architectural file into an accurate, efficient energy model that saves you time. And finally, reference the standards. Always know precisely where to locate all required input data, from ASHRAE and ISO handbooks to standard EPW climate files. This commitment to authoritative sources is what makes your model more credible and your results more defensible. We built a strong foundation today, but the field of VEM is always evolving. If you want to continue leveling up your skills, here are 3 advanced topics to explore. First, look into model calibration and uncertainty. It's one thing to build a model, but true experts know how to test it. Calibration is the process of using real-world utility data to tune your model's inputs, like schedules and infiltration, until the simulation results match the actual building's performance. You then quantify the prediction error to determine the model's reliability. Next, dive deeper into thermal breach modeling. While we simplified these losses in this module, heat loss through structural elements like floor slabs or balconies can be significant. This requires using specialized 2D finite element software to accurately calculate the linear thermal transmittance for these junctions before feeding that loss back into your VEM tool. Finally, explore computational fluid dynamics, coupling the VEM with these models. So we discussed that a thermal zone assumes perfectly mixed air, but that's not true in complex spaces like large area or theaters. CFD coupling allows you to link your zone model with a detailed fluid dynamic simulation, giving you a high-resolution view of air movement and temperature stratification. And with that, we conclude the Modeler's Toolkit. Thank you so much for watching this video and have happy modeling. See you in the next one. Bye.